All right, this is the first hour of Physics 1B for November 15th. Today we're going to be talking about refrigerators, heat pumps, something called the Carnot engine, the second law of thermodynamics, and entropy. So let's get into it. A lot of things, and hopefully we can do it all today. All right, so the first thing we're talking about are refrigerators. Okay, so you all probably have refrigerators in your homes, I assume. And they are effectively a heat engine operating in reverse. That's pretty much what these things are. So we talked last time about heat engines, and a heat engine was something that took in heat and then outputted work, basically. So a refrigerator is going to do exactly the opposite. It is going to use work. It's going to take in work. It's going to use it to dump heat out of its system, okay? So it's a heat engine acting in reverse. And over here on the left is kind of an energy flow diagram similar to what we had for the heat engine. And so over here you have the inside of the refrigerator, which is the part that you want to keep cold. And from the inside of the refrigerator, you're having some heat QC that is coming out. You're basically pushing it. It's taking in this heat and it's taking in work, and then it's using that to output heat into the outside air. So what happens is that the refrigerator cools down by just dumping hot air into the outside. And this happens through a bunch of coils that are on the back of the refrigerator. If you look at the back of a refrigerator of any kind, whether it's like a mini fridge or whatever, you'll see a series of coils that look, I guess, something like this right here. And that's where they're dumping out the heat. Oh, sorry, this is the air conditioning picture, which is basically the same concept. Let's pull this up here. There's a lot to take in on this diagram. I understand that. But over here is a picture of the refrigerator, and these coils back here on the back is what I was talking about. All these they're usually dark colored. Okay, so this is going to go through all the pieces of the process, but I just wanted to pull this up to show that the hot air is coming out here, basically. Okay, let's talk about the math of this. So in this picture, if this is our system, right? Think of the circle right here to be our system. What would the sign of QC be? Is it going to be positive or is it going to be negative? Is it less than 0 or is it going to be greater than 0? QC is positive because the heat is going into the circle, right? Just from whenever heat goes into the system, it's positive, right? When heat goes out of the system, it's negative. So QC is positive and QH would be negative, right? And what about W? Work in this case is being done on the system. It's going into the system. So should the work be positive or negative? W would be negative, exactly. Because when the system does work, it's positive. When work is done on the system, it's negative, right? All right, so we can take all of these together and write down this equation. And if we want to write it in terms of like absolute values, we can write it like this. Oh, this would also be absolute, my bad. And now the next thing to talk about is efficiency of a refrigerator. So with the heat engine, our efficiency was just the amount of work that was done divided by the heat input, right? Just to remind you, the efficiency for the like a heat engine was work done divided by QH, I believe, right? Because, yeah, you always input more heat than you get work out. So that defines efficiency for an engine. For the refrigerator, we're going to define something called a coefficient of performance. So coefficient of performance, which is going to be a measurement of how much... Oh, my handwriting seems really bad today. I don't know why. All right, so the coefficient of performance, we're going to use the symbol K for that. And for this is basically going to be equal to the amount of cooling that can occur, which is going to be equal to the amount of heat that you can actually pull out of the refrigerator, divided by the work that you have to do. Okay, and using the above equation here, we can replace the work by moving QC to the left-hand side. So this is going to be QC over, sorry, that's hard to read. Let me read that. QC divided by, the work is going to be QH minus QC. So that would be your coefficient of performance. However you want to write it. Either way. Yeah. So that's going to be one of the things that we can calculate for a refrigerator. And yeah, the more heat you can dump out for work that can be done, the better. I think this number could be greater than 1. Yeah, I don't see why not. I think this number can be greater than 1, right? I guess we'll see. I don't really know. Definitely not an expert on this kind of stuff. But I'm pretty sure that K can be greater than 1. Okay, so let's look at this picture and let's talk about how this actually works and see if we can make some kind of understanding of it, okay? So here's a picture that's another kind of a schematic of what's going on. There's the inside of the refrigerator is here, and you've got these tubes that are all connected up. You can see one side of the tubes is cold, one side of the tubes is hot, and then they have a compressor right here. So let's see exactly how this is working. All right, so let's start from number 1, I guess, right? So it says the compressor takes in refrigerant fluid, does work on the fluid to compress it adiabatically, and then delivers the fluid to the condenser coil. Oh, that's a lot of words. That's a lot of words. When it's delivering to the condenser coil, it's delivering it over here. So it expands it? No, it compresses it. Okay. So it does work on the fluid to compress it. So here's work being done. This is the external work that's being put into the system by this compressor. It compresses it, sends the fluid into these pipes over here. It comes out as, since it was compressed, it comes out as high pressure and it's hot. So the condenser says, okay, then we go to 2. Compressed fluid in the condenser is at a higher temperature than the outside air. So the fluid gives off heat to the air, which partially condenses to a liquid, that causes the fluid then to partially condense to a liquid. Okay, that makes sense, because if this is hot and it's at, like, let's say 100 degrees Fahrenheit and the outside air is at 70 degrees Fahrenheit, then heat is going to come out of the system here, basically. And in doing that, it causes condensation. Okay, then we go through the expansion valve. It says the fluid expands adiabatically through the expansion valve. What does that mean? Does that mean you just give it room to expand? I don't know. Let's go on to 4 and see if that makes any more sense of it. So the fluid's allowed to expand. It says after expansion, the fluid in the evaporator is at a lower temperature than inside the refrigerator. So something happens between here and here that the fluid is now colder than the fridge. So the fluid now absorbs heat QC from the fridge. So if the coils are colder than the fridge, then they're going to absorb heat. That cools the contents of the refrigerator. And the fluid partially evaporates to vapor. And then it goes out here. It returns to the compressor so another cycle can begin. So I guess by this point, the fluid has... So it's evaporated to vapor. So it's back to vapor. It's low pressure, and it goes through the compressor, which makes it high pressure. and then repeats the process all over again, using the same fluid over and over again, right? So that's a refrigerator. Fluid, yeah, okay. Did that make any sense? Does anyone have any questions about that? I would have a lot of questions. The liquid heats up just from being compressed. That would seem to be the case, yes, Troy. It takes in refrigerant fluid. It does work on fluid to compress it adiabatically and delivers the fluid to the condenser coil. It does seem that process is what's causing it to heat up. And I mean, yeah, exactly. I mean, it says refrigerant fluid. This fluid seems to be in vapor form and liquid form at different stages of this. It seems like in the condenser stage, it's in a liquid form, and then when it gets to the evaporator stage, it's in mostly a vapor form. But it does say it's kind of a combination of each. Either way, at the end of the day, what is this thing doing? What it's doing is it has some device that can heat the fluid up, which allows it to dump. The goal here is to get it as hot as possible, right? Because then you can dump that heat into the external air while the fluid is flowing through the back coils, right? And then, it's flowing the other way, this way. So the fluid's hot here, so it can give off heat, but then when it goes into the evaporator, or this expansion valve thing, it cools down before it goes into the fridge. And now it's cooler than the fridge, so the fridge can take and use its heat to give back, and you get back to the compressor. This is where it heats up again. It's a pretty brilliant kind of idea that you can cool things down simply by moving a fluid around and making sure the fluid is hot when it's on the outside and cold when it's on the inside. That's ultimately what this thing does, right? Is the fluid's hot on the outside and it's cold on the inside, and it cycles through. And because it's cold on the inside, the hot food will cool down, and when it's hot on the outside, you can dump the excess heat that you absorbed from the food. It's kind of like an electrical circuit, actually. It's pretty cool. Water cooling system is the same thing. In a water cooling system, the fluid would just be water, right? Yeah. Same thing works for or the way that an air conditioner works is the same. If we get these both on the same page here. Drop my tablet. All right. With the air conditioner, the similar concept. You can see you've got a compressor and an evaporator here as well, and you've got this. So in this case, what you would have is this would be like a window unit, I think, the way that it's shaped at least, where this part is outside the window and this part is inside your home, and it does the same thing. It takes in warm, humid air this way, and then it dumps it out the other side, and it does so by the process of a fluid that's flowing through these tubes, pretty much. Okay, so those are refrigerators. Next thing we want to talk about, I think, is the Carnot engine, or second law. Okay. Yeah, the second law of thermodynamics. We briefly mentioned this at the end of class, but we'll talk a little bit more about it today, and we'll look at some special cases that tell us things about it. Okay, so the second law of thermodynamics states this right here. Okay, so let's just read it and make sure we understand what it says. So it says, it is impossible for any system to undergo a process in which it absorbs heat from a reservoir at a single temperature and converts the heat completely into mechanical work, with the system ending in the same state in which it began. So it's a lot of words. This is called the engine statement of the second law. The second law of thermodynamics doesn't just apply to heat engines, though. It applies to all systems. So it's a law of thermodynamics, but it applies to any system that you describe. And there are different ways of stating it. This is just one way of stating it. Now, to relate this to what we had kind of learned in the past. So I believe that when we talked about heat engines, I think we said that the work done by the heat engine, tell me if this is wrong, was equal to QH minus QC. And then as I mentioned before, we said that the efficiency of the engine was equal to the work that it could do divided by QH, the heat that comes in. Do those two look right to everyone? Okay. So another thing that this is saying, if we look at it, it says it's impossible for a system to undergo a process in which it absorbs heat. So absorbs heat from a hot reservoir. That's this. That's the QH, right? And then it's saying that it's impossible to convert that heat, the same heat, completely into work, with the system ending in the same state in which it began. So if this wasn't true, then it would be possible for E to be equal to 1, right? You could get an efficiency of 100% if this was true. If it wasn't true. What it's saying is that this is impossible. So you could summarize it all by saying that the second law of thermodynamics states that it's impossible to construct a heat engine that's 100% efficient. You can never get 100% efficiency. That's what this is saying. Another way you can state this is to say that it is impossible to construct a perpetual motion machine. Basically the same kind of statement. You can't have a machine that's 100% efficient. You have to be losing energy in some way. So, and why are you losing energy? You're losing energy because all known thermodynamic processes are irreversible. You take a firecracker, you set it on fire, it explodes. That's an irreversible process. You cannot get the energy back. And when you convert heat into work, part of the reason why you can't have 100% efficiency is because the process of the conversion of heat into work involves extracting energy from molecules that are moving around randomly. And the process of that extraction is never going to be 100% efficient because you just simply can't access all of their energy. And you're also not going to be able to go back to the original state without, Okay, that's the second law of thermodynamics. If we compare this to other things we've learned, the first law of thermodynamics was just, delta U is equal to Q minus W, right? That's an actual equation that we can use. The second law doesn't have an equation associated with it. It's just an idea that controls how certain systems and processes evolve. So we don't do calculations with it. It's just a statement so that we can understand the limits of these processes that we're talking about. Okay? Does anyone have any comments or questions? Yeah. I mean, we've been dealing with equations, but we've also been dealing with concepts. But yeah, I mean, the other thing I'm thinking about is if you think about Newton's laws, Newton's 3 laws, or you think about Kepler's laws, those are all mathematical in nature, right? The first law is less mathematical. It just says that, you can write it mathematically. You could say that when net force equals 0, that means acceleration is 0, so velocity is constant. The second law says net force equal to mass times acceleration. The third law says the force of one object on another is equal and opposite, so that's another equation. Kepler's laws are all equations. So it is very strange that you have this philosophical statement almost. In fact, there's been a lot of philosophical work that's done on the second law of thermodynamics. There's a whole field of like philosophy of science where people look at stuff, and the second law is a popular one. What does this say? Guess 2, I'm used to thinking, okay, what's the equation so I can memorize it? Yeah, this one's more about just having an understanding of what a heat engine is, having an understanding about what irreversibility means, and then putting those ideas together to make this statement. And I guess one other thing I should say is I didn't tell you why this is true. Like, how do we know it's true? And the answer is that experimental evidence. We've never been able to make an engine that's 100% efficient, right? We've never been able to construct a perpetual motion machine. And so it leads us to believe that this is inherent to these type of processes, that you're always going to have some kind of loss. Okay. There are other ways to state this, like I said. Another way to statement is it is impossible to have, for any process, to have as its sole result the transfer of heat from a cooler to a hotter body. Okay. So this is, okay, so the book calls this the refrigerator statement. It's also been referred to as the Clausius statement, but it's not really that important. The point from this one is that it's putting the second law of thermodynamics into a way of stating it that is, I think, somewhat obvious to us, if I can use that word. Or maybe the better word is to say that this turns it into a common sense statement. Because what this is saying is that you really can't have heat flow from a cold object into a hot object. And that's something we all know. It always goes the other way. The flow of heat is always from hot to cold. So there's no way that you can have a process that the only thing that happens is that a cold body has its energy flow into a hot body, right? As a simple example of this, and again, this is where I think this can be really obvious. Suppose that I take a chunk of ice, right, and I place it on a table. You all know that unless the place that I put the ice is colder than the ice, like unless I'm putting the ice into a freezer or something like that, if I just put it into just the open air, there's no way the ice cube is going to get colder, right? It's impossible. There's no way that heat can flow out of the ice cube and into the environment. The reverse always happens. The ice cube will eventually melt. That's also an irreversible process, because you're never going to reconstruct the ice into exactly its same form. So there's some pictures here that your book has for this stuff. Oh, maybe I put them over to the side. Let me see if I can find them. These ones here. Okay. So let's see if we can make some sense of this and see if it's even useful at all. Okay. So the engine statement was the first statement. Let's get back up here so we can see the statement. Let's see if this this picture makes any sense at all. Okay, so it says the engine statement of the second law of thermodynamics. We have this picture here. It's talking about a workless refrigerator. Okay, so it says if a workless refrigerator were possible, it could be used in conjunction with an ordinary heat engine to form a 100% efficient engine, converting heat QH minus QC completely into work. So what does this look like? Okay, so the workless refrigerator would be a refrigerator that took heat QC, dumped it to QH, but these two are exactly equal to each other here. So there's no work, there's only one QC. The QC that comes in is the same as the QC that goes out. That would mean your refrigerator is basically just dumping 1,000 joules of energy out into the environment constantly. Something like that. And then I guess what's being said here is you could then use the same two temperature differences to now take some heat QH out, turn it into work via a heat engine, and then dump the same QC back into here. I don't know if they intend to mean that these two QCs are the same. I'm not sure. Really not sure. Probably though. I don't know. It's probably not that important. Anyway, they're saying this would be equivalent to taking all of the heat and turning it into work. Boy, I gotta say, looking at this picture doesn't really make things clear to me. It just makes me more confused. Well, do you all understand this? Maybe one of you can explain it to me. If a workless refrigerator were possible, it could be used in conjunction with an ordinary heat engine to form a 100% efficient engine. Get the left side a little bit. What I think is really funny is, yeah, I think that's right, Troy. I think you're supposed to imagine kind of an engine and a refrigerator just using the same two sources here. The thing that's so funny to me is that it's referring to this as the engine statement of the second law of thermodynamics, but it's using a refrigerator to explain it. I don't know sometimes. To me, this statement isn't that hard to understand. It's just saying that every time you have a system, you can't turn heat totally into work. That's what this says, and this makes sense to me. You're always going to have to dump some of that heat somewhere. You just have to. Otherwise, you're not going to get back to the same starting point. Okay, let's look at this one. See if this one's more clear. So this is the refrigerator statement of the second law of thermodynamics. It says if a 100% efficient engine was possible, it could be used in conjunction with an ordinary refrigerator to form a workless refrigerator, transferring heat QC from the cold to the hot reservoir with no input of work. So we know that this is impossible, that you can't go from QC to Q. These two have to be different from each other, and there has to be work coming in as well. This one says you take the heat out of your 100% engine, you use that 100% engine to convert heat totally into work. The work is then used to power a refrigerator. Okay. Okay, so they're saying basically that if it was possible to have a 100% efficient engine, you could take that heat from the engine, turn it into work, and then now you have a workless refrigerator. Even though there's work being done on the refrigerator. It's workless, I guess they're saying, because the heat that came in, I don't know what they're trying to do here. It's using work. It's just that it got the work from somewhere that it shouldn't have. That's all that it's saying. That's all that it's saying. I feel like this just makes things more confusing. I don't know what you all think, but maybe it helps some people. I think we just jump into the Cardo Cycle. I don't know what they're trying to do here. I really don't. All right, let's talk about the Carnot Cycle. Do I have that one down here? Yes, I do. We do it on time. 10:16. We're doing fine. All right, the Carnot Cycle. This comes up in all the thermodynamics classes. Okay. So, as we said, according to the second law, no heat engine can have 100% efficiency. So, the natural question that arises is how big can the efficiency be? How efficient can an engine be? And our Carnot cycle is going to be the basis of what we call a Carnot engine. And this is going to be a hypothetical idealized heat engine that has the maximum possible efficiency consistent with the second law. Okay, so in order to make this work, we have to think about reversibility and irreversibility. We know that reversible processes tend to be more efficient in general. So in order to make this incredibly efficient, you have to get rid of the irreversible processes, okay? Yeah, Matthew says work being done to create a workless refrigerator. Exactly. Like what are they talking about? Like I don't understand sometimes. All right, that's not the point though. Okay, so the Carnot cycle is going to be the cycle for basically and kind of like an ideally maximally efficient engine. Sorry, I don't know if that actually makes sense. It's like an ideal type of... so the goal is to get to figure out what the maximum possible efficiency is. And then to do this, we have to basically try to avoid the irreversible processes, which is kind of hard to do. But we will do our best, and we'll see, what type of processes you need to have in order to do that. Okay. Mentioned a couple of other things here. Right. So any heat flow through a finite temperature drop is automatically irreversible. That means that we have to keep the system pretty much at the same temperature all the time. And I think that if you look at the picture on the right that we'll be talking about in a second, the idea is we have to keep the temperatures very close together. And we have to make these processes adiabatic. So that means that all processes in the cycle have to be, to avoid irreversible processes, we have to make it so that all processes are isothermal or adiabatic, because temperature changes are automatically irreversible, and right, it has to be adiabatic because any heat transfer would not be reversible. Okay, so let's go through and talk about the steps of the cycle. Okay, first of all, step one, right here. So what do we have? We have a ideal gas, and we have different PV isotherms in our diagram right here. So this is a pressure versus volume graph, and each line represents a different temperature. Okay, if you don't remember why that's the case, remember that if we write pressure as a function of temperature and volume, we get this equation from the ideal gas law. So the pressure is proportional to 1 over the volume, which is why these lines look like this. It's like y equal to 1 over x. And then different temperatures just correspond to different curves, with increasing temperature going up. All right, so we have this gas in the process A to B. So that's the process along this line here, AB. We have isothermal expansion. In this expansion, Q is equal to QH, so the heat that's coming in is greater than 0 and work is done on the system. So the volume increases. And you can see going from A to B, the volume is increasing. Okay, so here we're going to say that step 1 is that the gas expands isothermally. So it expands at the same temperature, at temperature TH. Doesn't say it up here. I'm going to write it on this one that this is our temperature TH right here. Okay, we can see it on the picture. If you look at A to B and you follow that line down, TH is written right here, but I'll put it on top of that so we're clear. So step is the gas expands isothermally at temperature TH, absorbing heat heat equal to QH. We want absolute value sense on that? No, we don't. Okay, and this is the step A to B. All right. The next step, going down to 2, is going to be adiabatic expansion. So now we're going from B to C. So now the temperature is going to change, but we're keeping the system so that it can't dump heat into its environment or accept heat from its environment. But it's expanding, so the temperature is going to drop. So from B to C, this is adiabatic expansion. And remember that adiabatic just means that no heat is going in or out. This is until the temperature drops to TC. So this is the part I don't understand really well here. So we said earlier that okay, that's the key thing. Heat flow through a finite temperature drop is an irreversible process. So you can't have finite temperature differences when there is heat transfer. But if there's no heat transfer, then we call that a reversible process. So the point is we want to make all of these reversible. And the claim is that adiabatic expansion, as long as the temperature can change, but as long as no heat comes in, we're going to call that reversible. Every time I talk about this, I've taught this topic for like 10 years or something. Every single time I talk about the Carnot cycle, I have such a hard time believing that this is realistic. You know what I mean? Like, I have a really hard time getting my mind around the idea that this adiabatic expansion is truly reversible. But we'll go with it for now and see what happens. Okay, so the next step, we got to go from C to D now. So step 3, this is going to be another isothermal point. So this will be isothermal compression. Isothermal compression. And this one occurs at TC. And it rejects heat during this process. Okay. The only way that it can be compressed and maintain a constant temperature is if it also rejects some of the heat. And so that's what's happening. And this QC will be less than 0 because it's going out of the system. Okay. And then finally, step 4, which goes from D to A. We're going to have another adiabatic term. This is going to be adiabatic compression. And this will occur, this is going to lead to it getting back to the initial temperature where, here, let's write these down. This was TC. This one is, well, this step TH goes to TC. In this step, it's at TC. And in this final step here, TC is going to go to TH. That's kind of the temperature change process. So adiabatic compression until it's back to its initial temperature. Let's keep the color the same. And that is your Cardo cycle. Different textbooks go about talking about this in different ways. I feel like this is the most bare bones explanation of the Carnot cycle I've ever seen. And it's because, think about what's going on here. In steps 2 and 4, you have adiabatic expansion and compression, right? But in steps 1 and 3, the gas is capable of taking in heat and dumping heat, right? So you have to like really ask yourself, how is that even possible? Because in order to have true adiabatic expansion, what do you have to have happening with your system? You can't have heat come in or out, right? So what has to be true of your system in order for it to be allowed to have adiabatic expansion? What do you need? I mean, like if you're constructing something like this, what would you need? It has to be fast, that's part of it, yes. That's right, Christian. It doesn't have to be an ideal gas, no. It does not have to be an ideal gas. But Christian's right, it has to be quick. What else has to be true? If it's truly not going to lose heat to its environment. If you go buy a cup of coffee and you don't, it has to be insulated. That's right, Astro Lover, exactly. So that means that in this step here, it has to be insulated from its environment, or what Christian says, if it occurs quickly, then that's probably okay. But realistically, if you really do want to construct something like this, then in these 2 steps, it would have to be insulated, right? But in these other steps, it's not insulated, right? You see that? It's not insulated because it's taking in heat so that it can expand isothermally, and it's dumping heat so that it can compress isothermally. So, I mean, other versions of this I've seen where you have to take the gas and you have to put it in different places. Like, the idea would be that if you're absorbing heat, what are you doing? Well, that means you're actually putting this in contact with a hot object in order to maintain its temperature, right? Otherwise, its temperature is going to change. And then for this one, you have to put it into contact with a cold object. Now, they're going to be really close in temperature, because the idea here is that you want the temperature difference to be very minimal in this case, but like the way I envision this is that you have to be moving the object into different places. It's like you put it in contact with a hot object, it expands. You then take it away from that and insulate it, and now adiabatic expansion occurs, and it cools, right? And then you put it in contact with a cold object, and now it compresses because there's this cold reservoir that it can work with. And then you insulate it again, and now adiabatic compression occurs. All of that information is just missing from this explanation. And maybe I, as the instructor, am supposed to give it to you, which I did. But, I mean, what are you supposed to think as a student? This is just all happening magically? Like, I don't know. Like I say, I feel like this is bare bones. I feel like I know that the Carnot cycle is like an idealized idea, but that doesn't mean that you can't have some bit of reality in it. Okay. Anyone have any contact? Yeah, I mean, it doesn't. They're putting a lot on you as a student to understand that you would just automatically assume that something like this is happening, I think. But what do I know? I've never written a textbook. It's going to be really hard. Okay, so let's look at some of the math for this. So we apparently did this. I don't exactly remember. But we know that... Yeah, we can just do it again. It's easy to do. So we're starting with process AB, where we have isothermal expansion. For isothermal expansion, can you all tell me, if you remember, what is the change in internal energy going to be for isothermal expansion? What's delta U if it occurs at the same temperature? I wouldn't be asking if it wasn't an easy answer. It's 0, right? Because for an ideal gas, internal energy only depends on temperature, so delta U is equal to 0. That means from our first law of thermodynamics, which says that delta U is equal to Q minus W, I think, that now that means that QH that's absorbed in this process has to be equal to the work that's done in that process. We'll call it the work along the line AB, because, right, if this is 0, that means that Q equals W. So we'll say that QH is equal to the work from A to B. And the work from A to B has to be, I guess, let's just do it again because it's easy to do. So it's going to be the integral of the pressure dV, and that's going to be equal to the integral of nR. Now here, the temperature that we have is TH, I believe. It's good that I actually wrote these on here so we don't have to think about it too hard. We know the temperature for process AB is TH, and we divide that by the volume, and then we integrate between these 2 points. So we'll call them, we're going from A to B, so we'll call it VA and VB. So we end up getting that QH, which is equal to WAB. Okay, I need to scroll down so I'm not writing so small. This is going to be equal to nRTH multiplied by the natural log of VB over VA. Okay, so that's our QH. We can say the same thing for QC. So if we look at process CD, then we can write exactly the same thing down, except now it's going to be QC coming out of the system. So there's enough room down here, we can write it. So QC, which is going to be equal to the work from, what is it, C to D, should be equal to nR, and now we just put cold temperature here, and then we have the natural log of volume D over volume C. Okay. We can then take a ratio of this. Oh, I should say that this one is negative. Okay, I'm really reluctant to put a negative sign on here. Oh, no. We can make it negative by doing this. If we flip the log, then we can multiply by a negative sign like that. Is everyone okay with that? Just flip, all I've done is the VD and VC, we just flipped them. Okay. And then I just want to look at something real quick here. So VD and VC. So here's D and here's C. So which one's bigger? VC is bigger, right? So this is guaranteed to be a positive number now, right? If VC is bigger than VD, and how am I seeing that? Just to remind you, this axis is volume, so this is bigger than this, right? If you look at where it hits the axis, the volume here is bigger than the volume here, so this is guaranteed to be a positive quantity, which means that QC will in fact be negative if we write it this way. So this means that we know, I've got room over here, right? That the absolute value, how do you even write that you know that it's negative? You just say QC is less than 0? Okay, you'd write it like this. QC negative is equal to QC. That's how you'd write it. Anyway, we know it's negative is the point. And now we can find the ratio of QC over QH. Let's do that over here. So now we can find the ratio of QC divided by QH. And that is going to be, QC is negative in RTC, natural log VC over VD. We're dividing that by positive nRT hot, natural log of VB over VA. Okay. Anyone have any questions so far? No? Okay. The whole goal of where we're going with this, by the way, is to answer the question, what is the efficiency equal to? Just to remind you what's going on here. Just to kind of summarize where we've been. The Carnot cycle is a maximally efficient engine. We're going to avoid irreversible processes. We take our system through these processes that we believe to be reversible. And the question is, what's the efficiency? So now we're at a ratio of QC over QH, which, if you remember, the efficiency of the engine is directly related to this quantity, right? It's like 1 minus QC over QH or something like that, right? Was our efficiency for our engines. So now what we really need to do is to iron out what these ratios are. And luckily, we know something about adiabatic processes. In an adiabatic process, we know that, what is it, TV to the gamma minus 1 equals constant. Again, this is just for adiabatic processes only. But we have a couple adiabatic processes that we can use here to say something about that. And what are they? Well, they're step 2 and step 3. So we can say, if we look at step 2, and we go from B to C, I don't want to scroll down too much. We can say that we're going from TH to CC, right? So we can say TH on one side of the equation, TC on the other side of the equation, and the volume is going from VB to VC, so we'll have volume B over here to the gamma minus 1 equal to volume C to the gamma minus 1. Let's see if we did that right. So at temperature hot, we're at volume B, right? Yeah, B is here, that's the hot temperature, and at temperature C, at temperature cold, we're at volume C. So that was correct. And then we can do the exact same thing for the other step, which is from TC to TH and D to A. So we go from TC to TH, and temperature cold is D, I think. Yeah, D is on the cold isotherm, and then A is on the hot isotherm. So VD goes here, and VA goes here. I'm just going to check to make sure that's true. So TC and VD should be together. So TC is here, and that is D, and TH should be with A. And then we need a ratio. We need ratios of VC over VD and a ratio of VB over VA, right? So we're just going to take these two equations and divide them like this. Our temperatures are going to cancel. I thought I switched colors, but I didn't. And then we have VB over VA raised to the gamma minus 1 is equal to VC over VD raised to the gamma minus 1. And if I have a ratio raised to a power equal to another ratio raised to the same power, then that tells me that we can just get rid of the power, and VB over VA is equal to VC over VD. And then, if we know that this is true, we can come back over here and say that, well, if VC over VD is the same as VB over VA, then certainly if I take the log of VC over VD and I divide by the log of VB over VA, you're going to get the same thing, right? That means that this whole thing cancels out. Obviously, the N and the R's cancel out. And interestingly enough, we get a really simple result, which is that QC over QH for a Carnot cycle happens to be exactly equal to the negative of TC divided by TH. And that is a nice and simple result. And we can use that to make a statement about the efficiency now, because if we know what QC over QH is equal to, then what we can do is we can say that the efficiency of our engine is going to be equal to 1. It would normally be 1 minus QC over QH. But in our case, that efficiency is also equal to, it would be 1 plus this, I think. That can't be right. It has to be minus, right? This is where things get confusing. What was our definition of the engine? Was it this? It had to be something like this, right? That was our efficiency definition? Does that look right to you all? Does everyone agree? Because if we take this equation here and write it in absolute values, it would be QC. That looks right. Richard, thanks. Okay. Sorry, sometimes I forget these things. Yeah, okay. So if I take the absolute value of both of these, this will just become TC over TH, right? Because it'll get rid of the negative sign. So then, yeah, the efficiency would be 1 minus TC over TH. Okay, so this is the efficiency of a Carnot engine. Efficiency of a Carnot engine. You could say it's the efficiency of the Cardo Cycle or whatever you want to call it, but and I think that the temperatures have to be in Kelvin, obviously. I think that's obvious, right? And it's kind of nice because it basically says that, you know, the efficiency of the engine depends only on the temperature of the heat reservoirs. The efficiency is large when the heat difference is large and very small when the temperatures are nearly equal to each other. And wait, is that true? Right, yeah. We want basically the bigger the difference between the hot and the colds, the better your efficiency of your engine is going to be. What would the maximum number you could get here? Theoretically, what is the maximum value you can get for the efficiency, and what would TC need to be, for example? You want TH to be as big as possible. So suppose that TH is like 50,000 Kelvin or something stupid, something really, really large. What would TC need to be? If you want to have a 100% efficient engine, what does TC need to be? Remember, 100% efficient is E equal to 1. If TC is equal to 0, then you would get an efficiency equal to 1. But guess what? This is impossible. You can't actually get absolute 0. That's not realistic. So that means that the efficiency of the Carnot engine will never be equal to 1. So the greatest value that E can be is like 99% or something like that. And I think that one thing you can say about the Carnot cycle is that this is the whole point of this was to figure out what the maximum possible efficiency you could get out of an engine is. And you might think, if you hadn't been studying thermodynamics, you might think that the efficiency could potentially, at least theoretically, be greater than 1, right? But what this is telling us is that even if you design a perfectly efficient engine where all the steps of all the processes seem to be reversible, even still, you can't get 100% efficiency. It is just hard-coded into the rules. And that is, in my opinion, it is really surprising. It's really surprising that, you know, in a very real way, this is like a mathematical statement of the second law of thermodynamics, right? The second law of thermodynamics says that it's impossible to construct an engine that's 100% efficient at converting heat into work, right? And this tells us that efficiency boils down to a temperature difference. And you have no way of making the second quantity here 0. So it is mathematically, theoretically impossible to make an engine. I assume you mean temperature. The farther steps of... no, it's not. The temperature of space is quite warm. No, you're fine. I understood what you meant. I think the temperature of space is like 3 Kelvin. So we've definitely produced temperatures on Earth that are much colder than that. But the thing is that when you're constructing an engine, you know, even if we met some alien technology, we met some alien civilization, and they had access to some, you know, extremely advanced cooling technology where they actually could get extremely close to absolute 0. Let's say 10 to the negative 30 of absolute 0. Let's say they could get extremely close to it. Whatever that technology would be that would produce such a cold system, you probably couldn't use it to power an engine because the energy you're putting in to keep it cold is so much greater than the energy you're ever going to get out of the engine. At least I would assume. So we're going to do some problems. Anyone have any comments or questions? Oh, we'll take a break here and then we'll come back and do problems. Anyone have any questions? Excuse me. Okay, let's take a break until 10:40. 10:57.